Swayam Prabha. Digital India. Educated India.
Okay, so welcome to this course, which is an introduction to turbulence. We shall start with a brief introduction, right, for a couple of classes maybe, and then move on to the questions like what exactly is turbulence, and then see, right. Okay, so starting with fluid as a continuum, I think that's what we will start with. Okay, so what I'm looking at is essentially, okay, so fluid as a that's how you spell it, right? I think you are aware of this word probably. Okay, you probably are aware of this. So essentially, let us discuss this for a little while, as an introduction. So I'm talking about fluid as a continuum. So I'm going to just sort of jot down a few things right in the beginning. So some very basic fluid concepts is basic equations, and what you mean even by a fluid, how is that different from a solid, is something that you should look up. I think it will be useful to sort of understand a lot of material which will be a part of this course. Okay, all that should be available online. So fluid as a continuum. So what are we talking about here? So fluid is essentially an aggregation of molecules, right? A fluid consists of several molecules. So then you know what a liquid is and you know what a gas is. Both are fluids, right? So two examples of fluid, basically what I'm talking about here is a liquid, right, and a gas, right? Now and both of these, so fluid is made up of several molecules, like I just said. So both liquids and gases are made up of molecules. But then what is the difference? What makes one fluid a liquid and what makes another fluid a gas? Right? It's easy to think right, from those lines, because the distance between molecules is very large compared to the molecular dia. Molecules are in a constant state of motion. Where would that fit in, that description? That would probably fit in for a gas, isn't it? So the fluid particles are, let's stick to molecules. So the molecules are more closely packed, okay, for a liquid. So let's write that down here. Okay, here molecules, we're talking about molecules. Closely packed, right? Now for a gas, however, the molecular distance is very large compared to the molecular dia. So here the distance between molecules is quite large compared to the dia of the molecules. Right. Now, molecules are of course always in constant motion, they are all in random constant motion. So then when we talk about the distance between molecules, so is that constant or is it changing, because the molecules itself are moving, right? So I think when we mention distance, is something like mean free path, is something that you know of. So we'll come to that a little later on. Okay, so that's what it is. So you have a liquid and you have a gas, both which are fluids, and both of which are made of molecules. But the way the molecules are distributed is different, because they are closely packed in a liquid, and in a gas they are more far apart, they are more spread out. Okay. Specifically, distance between the molecules is much larger than the dia of the molecules, right. So, given a volume, the number of molecules in it are given a volume, the number of molecules in it are continually changing. Well, we'll see what we understand by them. So, now in this scenario, just think about this. If this is the scenario, okay, especially for a gas, then how do we define any physical property? If you had to define, say, the property of, say, density, for example, right? Now, how would you define that? You know, distance is not same, the number of molecules at a given point of time is not same. Then how do we define that, right? How do we define the density of any material, of any fluid? How do we do that, right? So that's the question it comes in, and therefore this concept of, we come into this concept of continuum, right? So given a volume, given any volume of a fluid, the number of molecules in it are constantly changing. So let me write that there. Given a volume of a fluid, number of molecules are constantly changing, right. Might as well also write here that molecules are always in random motion anyways. Okay. Okay, what have you? Are in random motion. Okay. So, molecules are in random motion, and given a fluid, number of molecules are constantly changing. That is a scenario, right. So, then we definitely have to choose a volume, we definitely want to choose a volume, is that even possible? Can we choose a volume where at least, as the aggregate number of, overall the number of molecules is not changing, is constant. Okay, and is that even possible? Is that even possible? Given a large, say, this classroom, in a room wherever you are sitting, right? So, can I define the density as one property over that entire room? Can I say one value of the density, and that is the density at every point in the room? Is that possible? Right? And if that is not possible, right, then can we define maybe a smaller volume, where that is possible, where I can do that, right? But I need to do that because I definitely cannot, deal with a, volume where the number of molecules is constantly changing. So, I can't do that. So, we need to choose. So, what we need to do is we will choose, let us just say we choose. And what do we choose? We choose a volume where the number of molecules is nearly constant, in spite of, we basically choosing a volume in a given domain of fluid. So, let us just say this is this is a large volume of fluid. Okay, this is a huge volume of fluid, right? It should be having no boundaries anywhere, right? Just think of the atmosphere or something. Okay, so then here I cannot define one particular value of density. So, then what I do is I choose maybe a volume, something like this. Okay, I choose this sort of a volume where, of course, there is interchange of molecules. Molecules are all in random motion, so they come into this region marked red. This is my volume that I am thinking, volume of, say, this is volume V, right? And there is constant interchange of molecules in and out of this volume V, but nearly but that the number of molecules inside the volume is nearly constant, right. So, although there is interchange of molecules, right. So, across the volume here, the number of molecules is nearly constant. So, here the number of molecules is nearly constant, right. So, that is what so this is a sort of volume that I am defining. Okay. Let us talk a little more about this volume. Okay. Now, if this volume, now the thing is I need to get a physical feel for how big or how small this volume can be, right. Now, this volume, if it is sufficiently large, right, then there is a chance that this is possible, the number of molecules is nearly constant, right. So, let me give you an example of that. Okay. Let me give you an example of that. For example, let us go to a new page. Okay. Now, for example, if I have a volume which is like this is my large volume, right, and these are all the molecules, right, these are all moving around, these are all moving around, okay, random motions, there is molecular motions, okay, something like that, say these are all molecules in a gas, so on and so forth, etc., etc., etc. Okay, right. Now, what sort of size of a volume should I choose? What sort of a volume should I choose? Now, I could choose a volume like this much, just say like that. The number of molecules in this volume is going to change, okay, because these molecules that you see here are all moving around, okay, and they're moving around and they're going in and out of this boundary that I have said, So, let's call this as A. Okay. So, this is a little volume that I have. I could have another volume which is something like this, right. So, let us call that as B, right. So, now this is another volume and the number of molecules, for example, A has just 1 in there and 1, 2, 3, 4, 5, so about 7 molecules then in B, right. That is going to change, because this is constant interchange of these molecules, they are constantly moving around, it is going to change, right. So, which one should I choose? Which one should I choose, A or B? Or for example, maybe I could have a domain something like this, maybe something like this, right. So, this could be a domain as well, C, right. Now, so the idea is, right, is if this volume is large enough, right, if it is large enough, then the number of molecules in it at a particular time is not going to be negligible, right. You are covering more space. So, basically it is not going to be negligible, right, and there is sufficient molecules in there, so that so you can define a physical property, which kind of represents the entire domain. We will get to that in a little bit. Okay. Now, I could take again, and let me draw one more, okay, and I could also have a volume like this, or for example, this much. Let us look at this D. E doesn't seem to have anything, not a single molecule right there, but then it will change. In another instant of time, it will immediately change, because there will be some molecules crossing the boundaries and getting in or getting out, right. If I have a domain, if I have a volume which is so small, with D, right, which is really small, then what do you suspect? Here basically it can contain probably a single molecule, maybe 2 molecules at the most, right. I am making it that small, this is my choice. So, I am making it that small. So, in this case, if it is that small, right, the molecular the behavior, each molecule's behavior or the variations is not going to be insignificant. That's going to be dominant. That's going to be dominant, right? So, for example, so what I'm trying to say here is that, for example, for this volume, say D, right? It is small enough. It is very small. Okay, it is very small, right? Such that what do I mean by here? That molecular variations are significant. Okay. So, how each molecule behaves, each molecule's variations, is going to be significant for, say, a volume like D. But if you take a volume like C, then what happens? If I take a volume like C, it has sufficient number of molecules such that I can take their property as a whole. I can take all of their properties as a whole, right, and define it as an average, right, for this entire volume. And therefore, I could probably have a density value, which is a single value and which you can use over the entire domain of C. Right? For example, if I gave you a glass of water, what would be the density of water there? You would immediately say 1000 kg per meter cube. Why would you say that? Right? So, that is a kind of domain, that's the kind of definition that we are looking for. So, this is the concept, this is essentially the concept of continuum that I am getting at. Okay? So, volume C essentially has sufficient number of molecules, right, and this number say, just to give you, to make it, give a crude example. So, it has, say, at an instant of time, it has, say, 100 molecules. So, the next instant is had, say, maybe 98, 99, but it is sufficient, this number is sufficient to define an average, right, value of any physical property, which represents the entire fluid, right. So, I am talking about a fluid density. So, that density, each molecule may behave differently, right, but I am looking at a macro property here. Okay. But then that macro property, if I take the entire volume, if I define one density for the entire atmosphere covering the entire earth, that is not going to be very representative. So, I am going to try and cut it down where that will make sense. So, I am looking at a volume, which is something like C, where the number of molecules is constant at over a period of time. It is more or less constant. Okay? And please note that when I say the number of molecules of constant, molecules are constantly moving across this boundary. Right? This boundary is not physical. It's our concept of how we define, physical properties for a given fluid. So, the molecules are actually moving across this boundary at a very random pace and constantly. However, I have taken a volume which is sufficiently large enough such that the number of molecules which remain inside at a given particular instant of time is constant. Right. As a result of which, I can define, say, a property like density, velocity, etc., as a single value, as an average value of all these molecules inside here, okay, and that will represent the fluid. Okay. Okay. So, fine. Now, let me sort of write this down then. Okay. So, let us just say if I were to put it in like an equation form. Okay. So, let the given volume, okay, let the given volume is this. Okay. molecular mass. Okay. Then how do I define density? Molecular mass is delta m, like the mass of all the molecules inside the volume, delta V, right. So, then that is basically equal to mass by volume, right. But is there anything else that I should write here? This is the volume that I want to define, right. This is the volume I want to define. How big or how large can this be? So, let us just say this happens over a limit where right, and this delta V star. So, this the volume tends to a specific particular volume, right, and this I am giving you some values actually, right, for all fluids, okay, for all fluids at atmospheric pressure, right. This volume, so this volume at standard temperature pressure, okay, it contains molecules, right, and this is sufficient to define a constant gamma, right. This is constant density, any physical property actually. This is sufficient define a constant rho, I mean, okay. So, that is my density. So, that is what I mean, right. So, you can see that I have always wondered what is this continuum, okay. It has this similarity with the word continuous, but it is not continuous, right. So, in this context, so this is something which is I am talking about this in terms of being continuous, or is it a continuum, okay. Now, if you see here, if you look at this the domain C, that with the volume C that I just spoke about, the molecules are not equally spaced, the molecules are not equally distributed, right. They are not, obviously, they are in random motion, and the only thing is the number of molecules, right, are defined the number of molecules which are in C are nearly constant, okay. And this is and I gave you a little example, these are standard values. So, this volume where the number of molecules is constant. So, how many molecules? The molecules is 3 into 10 to the power 7. Okay. And what is the volume? The volume is 10 to the power minus 9 cube of a millimeter. Okay. So, that is the volume, and that is the corresponding number of molecules. And if I have a volume like that, right, then this is sufficient to define a constant physical property. In this case, I am talking about a density, which is this, right. Now, so this is basically a molecular view. So, what I have shown you here in this diagram here, the volume C. So, I have all these molecules spread out, and that is it, right. These are all the molecules which are spread out. And what is a continuum? Now, the moment I define a constant gamma, right. Now, if I were to look at a molecule, if I want to look at this as a molecular view, right, this molecule, etc., it is going to be different, right. But now, I have said that I am going to define a volume, which I am going to define a domain which has a certain volume, which has a nearly constant number of molecules, in a given instant of time. And using that, I am defining a constant physical property. When I say a constant, what does this constant mean? What does this constant mean? This constant gamma means what? Yes, over time, yes, gamma. So, one was it, does it change over time? Well, the number of molecules is changing over time, isn't it? Right, because they are in random motion. But that is what we said, that although there is molecular exchange across the boundaries, but over this domain it is nearly constant. Right. So, when I say constant gamma, I basically mean that for this entire domain C, it is a constant value. Okay. This density is constant, which means that I think now that I have defined one value of this density, that density is applicable, is the same anywhere in this domain, right. So, I can therefore divide this domain into smaller parts, very much smaller parts, right. But each of those parts will still have a density rho, because that is the density that I am talking about. Right. So, that makes this domain, when I look at this now, when I look at this space, I might as well just change the, okay, let me go to another page. Okay. So, let me just sort of redraw that. Okay. So, I have I have this domain. Right. I have the same domain actually, let me try and sort of redraw that a little bit. Okay, it's the same domain, it's the same C, I think we wrote like that, right. So, okay. So, we have all these molecules which are sort of spread around, okay, which are just distributed. Okay. So, this is nothing but this is the molecular view, right. What is the continuum view? The continuum view is that this is basically right. So, now you can chop this up into smaller parts, you can chop this up into smaller volumes, right. So, you could have that. So, this is the continuum view. Right. So, basically continuum view is where we disregard the individual molecular properties or variations, right. And why are we able to do that? Because we take again I am kind of repeating myself. So, why am I able to do that? Because I have taken a volume which is sufficiently large enough, well, where the bulk aggregation of the molecules is not going to be insignificant, and the number of molecules is going to be nearly constant. So, I am able to define a physical property, right, velocity, density, etc., viscosity, right, in such a way that here the molecular variations or properties is going to be insignificant, but the group, the behavior of the group of molecules together in this volume, that is going to be dominant. And when I take because when I consider the density, how do I consider the density? I do consider the total mass of the molecules in the total volume. I do consider that, right? And that, since the volume is constant and the number of molecules is constant, so therefore the density is also constant. Having said that, so when I do that, so I take the mass, the macro property like that, and then I can apply that physical property on any small domain I choose to make here, right. I could make any domains which is smaller inside, I could do that, I could do that, I could do this, etc., etc. I could do whatever I want. Yeah. I could do that. And that is where the concept also comes, okay. That is where they also, so this is the continuum view, okay. And so that is where the constant, and these are, in the molecular view, the small circles that I have drawn are basically molecules. So these are, okay, let me write that down. So these are basically molecules, okay. Now, what are these small little boxes that I have drawn here, or some sort of little domains that I have drawn here, right? So, this is where I am talking about a particle or infinitesimal element. Okay, you've heard these words, right? So, this is something which is a particle yeah, or you can also call it infinitesimal element, yeah, right. We say that all the time, but is an infinitesimal element or a particle the same as a molecule? No, we are not saying that. Why we are not saying that? Because when I say a particle or an infinitesimal element, it will have the same density that is defined for this whole sea. Then the density or the velocity, the viscosity is not going to change, right. However, if I go down to a view where I am looking at each and every particle, each and every molecule, then it is different. So, basically I am looking, we are getting into quantum physics at some point of time. Okay. So, we are not going there. So, we are looking at things from a continuum point of view, right. Now, this becomes important for a class in turbulence to understand, because in turbulence you will see that it depends on how you look at the turbulence. If you look at it, if you look more closely, so to speak, this also happens when you are zooming in, right. When you zoom in, then you see more detail, right. I guess what I am trying to say in a continuum view is that we do not want so much detail as is going to be presented by individual properties and variations of molecules, right. However, if we can remove, if we can ignore that much that much of detail, we can, however, look at macro properties which give a fair bit of knowledge and a correct bit of knowledge about the physical processes that that we are really trying to understand here. Okay. Okay, so let me give you a little more information. What we will do, once we do this, now we are talking about molecules. Let's think about this. Okay, we're talking about molecules. So, molecules are in random motion, right? Then how do you define, if that's the case, right? Then how do you envisage, for example, the flow over the wing of an airplane? How do you envisage the flow moving through a pipe, right, which is basically coming into your house, and you open your taps and water flows out through it, right? How do you define that? How do you define its movement? When you say velocity, what are you looking at? Are you looking at the velocity of each molecule? Is that what you're looking at? So, that is where the continuum view is what continuum concept of fluid as a continuum is what I am trying, this is what I am trying to introduce here. Okay. All right. Again, let me give you some more values maybe. Okay, so I think we are going to talk about something called a Knudsen number. Okay, so to do that, okay, let me give you some values here, right. So, now we are trying to understand a concept. So, we have to put some math into it, because we are in the business of calculating things, isn't it, and manufacturing things and building things. So, we have to put some math into it, right. Okay, so this is again, these are some conditions, these are some information, so which I will give you. So, air at atmospheric conditions. So, what I am talking about is air at atmospheric conditions. Okay. Okay, so here average spacing between molecules is that. Okay. And then you have the mean free path, which I was talking about a little bit earlier, right. So, the mean free path, right, which is usually denoted as lambda, okay, that is equal to 6 into 10 to the power minus 8 meters. Okay. So, mean time between successive collisions, mean time between successive collisions of the molecules, right, of the molecules is seconds. Okay. So, because now the question also arises that, I did speak about, like what is the smallest geometric length scale that you could go to, where this is not going to be violated. So, because where still you can define a constant value of gamma. So, you'll be like, because if I may just go back a little bit, just a moment. So, the question to ask would be that now we had defined, I am looking at C. Okay. Now, I am looking at C here. So, C was a domain where number of molecules is constant. Okay. Now, I am saying that I have defined a value of a physical property, and I say that I can divide it down again into particles or infinitesimal element. But here the question will again remain, okay, that how small can you get, because if this gets smaller than is small enough to be just about the size of a molecule, then your assumption is going to be wrong. It's not going. Then it will not have the density, the average density value that you're talking about here. So therefore, geometrically, I still have to define the smallest value of this volume that I can get to, right? So therefore, what is the smallest geometric length scale that we can actually endure, right? So that's what we're talking about here. So therefore, here this is for now. These are the properties of air. Okay, and let's just write here. Okay, this is for a general flow. Okay, the smallest geometric length scale. Right. So, that should be greater than 10 to the power minus 4 meters, right. Okay. Now, if you look at this, right, now if the flow velocity, for example, so this is the length scale we are talking about, so that length scale is 10 to the power minus 4. Okay. So, which means that if the for example, if the flow velocity is say 100 meters per second, right, what should be the time scale for that sort of a flow, which should be basically 10 to the minus 6 seconds, right, time scale velocity. So, you define by that. Okay. Okay. So, now you can see how large or small this is, right. So, we use therefore the Knudsen number, right, for the separation of length scales. Length scales become very important in a turbulent flow understanding, because you will see slowly that there are behavior in the turbulent flow which is not going to be very dominant when the length scale is of a certain size. That sort of a behavior is happening only at a very small length scale, when you say the whole flow is turbulent, that does not mean that there is interchange of energy at everywhere. Interchange of energy is happening, but in a certain pocket, in a certain smaller length scale. So that's why talking about this becomes important, and that is why I'm trying to start with this. Okay. So Knudsen number again is used for separation of scales. So okay. The Knudsen number, okay, used for separation of length scales. Okay. And what is that? So, this is nothing but, makes sense, I think, right. So, this is the mean free path, right. This is the mean free path, which is basically the path which is traveled by a molecule between successive collisions. I think I am trying to remember, if I am wrong, to correct me. Okay. So, this is the mean free path. Okay. So, basically the molecules, one is going to collide and then they are going to go and collide with somebody else, right. So, it collides, then it travels certain distance, goes and hits somebody else. So, that is the mean free path, free, right. So, it's a mean path which is free when it is traveling from hitting one molecule to another. So, it is free at that time. So, you take all the values of all of that and take a mean of that. That is the mean free path. Okay. So, mean free path is the lambda, right, and L is the smallest geometric length scale that I can get at, which is this, right. So, in this case, for the general flow that if you have said smallest length scale that we are looking at 10 to the power minus 4 meters. So, if this is the case for this particular case, then here I can say the Knudsen number for this particular case, right. The Knudsen number is basically equal to 6 into 10 to the power minus 8 by 10 to the power minus 4, right, and this is equal to 0.6 10 to the power minus 3. Right. So, which is essentially, what does this mean? This essentially means that the length scale is 3 times order of magnitude larger than the mean free path, isn't it? Okay. So, that is that. So, what we are basically trying to say is that I cannot, so therefore, this is the Knudsen number, which is this, right. So, Knudsen number is essentially, so this has to be less than 10 to the power minus 3. So, therefore, it has to be less than, the Knudsen number has to be less than 10 to the power minus 3. Okay. So, in continuum approach, okay, so we just take the Knudsen number to be less than or equal to 1 actually. So, if you see this, that is the Knudsen number. So, basically the Knudsen number is less than 10 to the power minus 3. So, now in continuum approach, okay, I can write it here. Do you agree, or does it make sense? Think about it, the continuum approach, right, Knudsen number is less than or equal to 1, right. What does that mean? If it was equal to 1, then lambda would be equal to L, right. That is, mean free path is equal to the geometric length, right, but it is less than 1. So, lambda is less than L, right, which means the geometric length has to be at least higher than the mean free path, right. So, I mean, yeah, geometric length. So, therefore, the Knudsen number is going to be. So, unless and until that is possible, then you are not going to be able to use the continuum approach. So, it has to be more than that. Makes sense, that is what we said, right. So, if you are making your infinitesimal particle or to hold one molecule. So, if it can hold one molecule or two, then there is no point, right. So, continuum approach in this, the length scale at least has to be here L lambda by L, it has to be at least greater than the mean free path, right. Then you can say this is a continuum approach. What do I mean by that? Let me just just say that one more time. So, because what we are saying is here that the Knudsen number is less than 1, which means mean free path by least geometric length is less than 1, right, which essentially means L. So, the smallest geometric length scale has to be larger than the mean free path. Makes sense, right. So, only then, so that's how small you can get, right. So, when I ask the question, or when you should ask the question that you have this domain C, I have defined in such a way where macro properties can be defined, it is a single value, right. So, this is the continuum. Now, that single value can be defined on smaller parts of this continuum, anywhere it will have the same value, and a green little box particle here, infinitesimal element here, basically represents the entire domain C. It represents that domain, right. The question is, how small can green or this red or whatever they can be, how small they can be. So, the point is the least geometric length scale that you can get to has to be larger than the molecular mean free path, right. So, that is how small you can get. You cannot have a length scale which is less than that, then your continuum concept is not going to work, okay. Then it does not work. Okay. So, I think I am going to do a little bit and then sort of yeah, we will have to stop. Okay. So, yeah, so I think I have said this earlier. So, density is a macro property by summing the weights of. So, it is interesting now so therefore, one should remember that when I say density, right, what do I mean by density, right? How is density different from molecular mass? There is the molecular mass. How is density different? Because the density is an average value, yeah, by summing up the molecular masses of a group of molecules, right, over a certain volume. So, now in the continuum, and then this density is going to be a single value, right, which is going to be defined on every part of the domain, right. So, now our question was, how do we define the sizes of this? How do we define? Because the molecules are in random motion and they are constantly moving. So, if I take a certain little box, the number of molecules are also not constant. So, we had to define a certain volume, and we found that that volume for at atmospheric pressure is about 10 to the power 9, right, for all fluids, and it contains nearly 3 into 10 to the power 7 molecules all the time. So, then this is sufficient to define a constant density. So, density is a summation of the molecular masses of a group of molecules, right, group of molecules over a certain volume, and the number of molecules and volume is these are the values which are standard values. Okay. Okay, so I think we should okay, we will stop here and we will take it up next class. See, so the point is now we will have, when we are talking about turbulence. So, the turbulence will come only if a fluid moves. So, the important thing is when something is moving, how do you look at it, right? Right now, am I moving? Well, depends. If you're sitting on Mars, if you look at me, yes, I'm moving, right? But if you're sitting on Earth, you will see, no, I'm not moving, right? When you're sitting inside the airplane, you're not moving, but somebody seeing from outside knows you're moving. You're going from one place to the other. So, therefore, we need to look at the flow in a certain way. Again, how basically we're talking about reference frames, and that is a Lagrangian way of looking at it and an Eulerian way of looking at it.
Now, having said that, okay, in the continuum approach, right, that we've talked about so far, we've described the Knudsen number, and we've said that for a continuum approach to be applicable, Knudsen number, which is lambda by L, should be less than 1, lambda being the mean free path, right? And L being the smallest length scale. Okay. Now let's see if there is some, is there somewhere this continuum approach can fail, or are there places where, this description of the continuum approach can actually not be applicable. Okay, so in order to do that, let me just talk about some of the lengths. Give you some numbers basically. Okay, so let's do that. So let's say height above sea level and the lambda at that place. Okay, so at standard sea level, lambda is about 2.1 into 10 to the power minus 7 feet. That's small enough. As we go higher up, 50,000 feet, it's 1.2 10 to the power minus 6 feet. At least 10 times more, right? At 200,000 feet, it's 9.1 and 10 to the power minus 4 feet. So the mean free path essentially is increasing quite rapidly. At 400,000 feet, it is about 24 feet. Interesting, right? So the mean free path at about 400,000 feet is 24 feet. Okay, so there's no way we can use the Knudsen number the way we've written it here and use the continuum approach at 400,000 feet. Okay? So at 400,000 feet, this description of the continuum approach is not going to be applicable, right? So that is essentially to say that except for extremely high altitudes, right, or for flow past very small objects, extremely small objects. So L is basically tending to a very small number, making Knudsen number very, very large, right? So then also, if you keep those situations separate, then we can use continuum approach. Then continuum approach is going to be applicable. So at standard sea level, maybe even 50,000 feet, continuum approach is applicable. But other than that, if you sort of go way higher up at higher altitudes, continuum approach is not going to, it's going to fail, or it's not going to hold true the way we've described the continuum approach. Okay. Now, having said that, the Knudsen number is still a model, is still a mathematical model, right, to approximate a group of molecules, and it depends on Reynolds number and Mach number. And I'm going to use this paper here, and I'll give you the reference. This is a where we are looking at, some the limits of the continuum approach. Okay, so if you look at, say, figure 2, right? So if you look at figure 2 here, so you have this solid line here, right? And the x-axis is the Reynolds number, and the y-axis is the Mach number, right? And the continuum approach is applicable in the space which is to the right and to the bottom of this solid line, right? So if you see for say Mach number less than 0.1, right? Mach number less than 0.1, and Reynolds number less than 90. So that's the the crossing of the two lines that you can see there, the dotted lines, right? So that's the area. So the continuum theory breaks down for boundary layers, right? So that's why we have the boundary layer limit, right? So that's the place. So for Reynolds number less than 90 and Mach number less than 0.1, the continuum theory breaks down for boundary layers, okay? As is shown in this plot here. Let's move on to another figure here, which is figure 3. Now we have the maximum Knudsen number on the y-axis and the Mach number on the x-axis, and you can see here too, okay, the continuum theory fails for Mach number less than 0.1, okay, and Knudsen number less than 0.008 for boundary layers. Okay, that's the boundary layer limit. So that's something we can see from this plot. Again, let us look at, say, a figure 5 here. Okay, so the x-axis is the Reynolds number, and the y-axis is the maximum Knudsen number, and all these lines are basically at various Mach numbers. Okay. Now, for example, at a Reynolds number of, say, 100, okay, Mach number is 10 to the power, say, minus 5. The maximum Knudsen number is 0.001. Okay, so in other words, at this Reynolds number, which is 100, and Mach number, which is 10 to the power minus 5, continuum theory is going to be violated if Knudsen number is greater than 0.001. Okay, that's what we can sort of gather from here. Okay, so now for example, in the range, Reynolds number is greater than 0.01 to Reynolds number is greater than 0.01 and less than 100. Okay, and Mach number is 10 to the power minus 5. Knudsen number, maximum Knudsen number is 0.001. So hence, in this range of Reynolds number and at the corresponding Mach number, continuum theory is going to be violated if Knudsen number is greater than 0.001. So this is the reference that I've used the class from. So Limits of Continuum Aerodynamics, John F. Aircraft, 2010, by W. F. Phillips, Utah State University. Okay, so this is the reference that I've used, and you can sort of get it online and look at it. Okay, and if you can't, then I can sort of I downloaded it from the net. It's possible.
So we'll get to that in the next class. So I'll close today, and we'll meet up in the next one. Okay, thank you.